This video is part 3 of our lecture on virtual memory, and we're going to continue talking about topics within, like thrashing. If a process doesn't have enough pages, the fault rate is very high. The page fault, to get page, we replace the existing frame, but quickly need the frame back. This leads to low CPU utilization, the operating system thinking it needs to increase the degree of multi-programming, and essentially when another process is adding to the system, things get really bad because it'll keep bringing in more processes. Basically, that's called thrashing, when a process is busy swapping in and out pages. CPU utilization drops to the floor as thrashing increases. Demand paging and thrashing. Why does demand paging work? When using locality mode, processes migrate from one locality to another, and localities may overlap. Locality means locality of reference. So one of the ways to help with this is what's called a working set model. Let's say delta is defined as a working set window, and that's a fixed number of page references. For example, 10,000 instructions. The working set of process P is the total number of pages referenced in the most recent change in time. If the delta, the change in time, is too small, it won't encompass the entire locality of memory. If it's too large, we'll end up with multiple. If it's infinity, we'll encompass the entire program. So D equals the sum of working set processes, frames over, and that's the total demand frames. If D is greater than the number of frames, we'll see thrashing. So how do we keep track of the working set? We can approximate it with an interval timer and a reference bit. For example, if delta equals 10,000, the timer interrupts after every 5,000 time units. We keep in memory 2 bits for each page. Whenever a timer interrupts, we copy and set all the values of the reference bits to 0. If one of the bits in memory equals 1, the page is in the working set. Why wouldn't this be completely accurate? Because we might have more pages in memory in our virtual memory system that are usable. So if we could instead increase it to 10 bits and interrupt every 1,000 units, we'll get better performance. The other approach is page fault frequency. We establish a acceptable page fault frequency rate and use local replacement policy. If the rate is too low, process loses frames. If it's too high, the process gains frames. So there's a direct relationship between the working set of a process and its page fault rate. The working set changes over time, and here you'll see examples of the peaks and valleys. So memory mapped I/O allows file I/O to be treated as routine memory access by mapping a disk block to a page in memory. A file is initially read using demand paging, and a page-sized portion of the file is read from the system into a physical page. Subsequent reads and writes are treated as ordinary memory accesses. This simplifies and speeds file access by driving file I/O through memory rather than read and write system calls. We lose the overhead of having to go into kernel mode. This also allows several processes to map to the same file, allowing the pages in memory to be shared. But when does written data make it to disk? Either periodically or when we close a file. So, for example, when the pager scans for dirty pages. So here are some memory map techniques for all of I/O. Some operating systems use memory map files for standard I/O. Processes can explicitly request memory mapping a file via mmap in Linux. Now the file is mapped into a process address space. For standard I/O, nmap works appropriately. But it can also map into a kernel address space, and the process still does reads and writes in kernel address space. It can't handle the memory using memory mapped I/O. Memory map files can be used for shared memory again, but we use that via system calls. And again, here's an example of what it actually looks like. with processes, and each process pointing to virtual blocks which talk to actually the disk file. We can share memory via memory map file, because then we use our shared map in the memory map, and it can back itself automatically as well. All right, in Windows API, we create a file mapping and then establish a view of the map file. So the producer would create a shared memory object and open the file via create, and create a mapping via create file mapping, and that creates a named shared memory block. Okay. When we allocate kernel memory, we treat this differently from user memory. It's often allocated from a free memory pool because we would like to keep our operating system structures in memory. Also, there are certain kernel memory blocks that need to be contiguous. For example, for a device I/O, you don't want to be reading device from a hard drive and having it run back and forth across all different blocks in various parts of memory. Okay, there are different types of allocators. There's what's called the slab allocator, where it's one or more physically continuous pages. The cache consists of one or more slabs. The single cache for unique kernel data structures. Each cache is filled with objects of the data structure. When the cache is created, we mark our objects as free. And when they're used, we mark them as used. If it's full of objects, we create an empty slab. So a slab is like a region of objects. There's no fragmentation and fast memory allocation. So here we have our caches that talk to various slabs, but this is already physically allocated. So sometimes we pre-page to reduce the number of page faults that occur at process startup. All or some of the pages the process will need can be pre-paged before they're referenced, but if pre-pages are unused, I/O in memory was wasted. So we want to be careful to keep our page loss near to zero. Sometimes OS designers have a choice, especially if running on a custom-built CPU. Page size selection must be taken into consideration. We must also take into consideration fragmentation, page table size, I/O overhead, number of page faults, locality, the TLB size, and effectiveness. We should always make this a power of 2 to talk about interlock. Sometimes pages need to be locked into memory. I/O pages that are used for copying a file for the device must be locked from being selected for eviction. Otherwise, we won't be able to write things successfully. So we have to allow pinning. Okay. Windows uses demand paging with clustering. Clustering blinks pages in surrounding to the faulting page. Processors are assigned a working set minimum and a working set maximum. Working set minimum is the minimum number of pages guaranteed. A process can have up to the maximum. When the amount of memory in the system falls below a threshold, the automatic working set trimming is performed to restore the amount of memory. Working set trimming removes pages from process that have pages in excess of their working set. Okay, we're not going to talk about Solaris because it really isn't an active operating system anymore.